Welcome, and we'll continue our organic chemistry lecture where we left off. Now, so we're talking about the properties of all these acid derivatives. And so the question you may be asking, this is a lot of different functional groups looking at all at the same time. Up until now, we've just done, just do a whole chapter on alcohols, do a whole chapter on ethers, chapter on alkenes and ketones and amines. Well, we're going to look through a lot of different reactions here, but a lot of these guys are interrelated, and the fact that they can actually be interconverted with relative ease is going to be part of why they're all in the same chapter together. It's going to be a class of compounds where they can all be moved back and forth without too much difficulty. So let's start off today by looking at the basic reaction, which is called the interconversion of acid derivatives by nucleophilic acyl substitution. So essentially, acyl transfers or acyl substitutions, which works on addition-elimination mechanism. The general mechanism is that we have some sort of functional group. We have some sort of functional group. We don't know what it is. We're not being very specific. It's some functional group. We have a nucleophile. Comes in, attacks the carbonyl. We get our intermediate, which is occurs from the addition. Here up here. And then we see then that's up. Now that lone pair is going to come back down and kick off our. It's reversible, so we can put it back where it is. It's the same general premise of what we did with organolithium, the carboxylic acid, that we attacked there, moved it up, and then kicked it back down and got an aldehyde. We got some sort of like ketone. So nucleophiles now bound, and we have our leaving group. So the same general mechanism is going to be used in a lot of these guys. So clear this out, but so you see it's adding, kick it up to intermediate, move back down, and then eliminating. We're not eliminating and adding, we're adding, then eliminating. So now we can classify these. So we have our acyl chlorides at the top, our anhydrides are esters, our amides, and our oxalates, which is the deprotonated oxygen. As we're going up, we have reactivity. So let's look at the leaving group. Leaving group for each of these guys in this reaction. Leaving group of this guy would be a chloride. Then you have a oxalate. Then you would have a oxide. Then you'd have an amide. Well, not amide, but the deprotonated amine. And then finally, this guy would be 2 minus. And we look here, we have basicity. We see this trend right here, that as we go up in reactivity, the basicity decreases. Strong bases are good nucleophiles, as long as they're not bulky. They're good nucleophiles. So this guy will not leave at all. This is not going to be a leaving group. That is so strong of a base, it is not going to want to leave. OH minus, maybe. Not likely. So this guy is very basic, a little bit less basic, a little bit less. This guy's pretty stable. That's actually the conjugate base of a weak acid, and that a salt. So you have here, we're looking at, see the reactivity here, inversely related with the basicity. Now, yeah, that's right. So not only is it going to be related to the basicity, but it's also going to be related to the resonance stabilization of the acid derivative. This guy is very strongly resonance stabilized, thus not likely to lose. This is moderately strongly resonance stabilized. Again, would be putting a positive charge on the nitrogen. Can happen. This would be putting positive charge on the oxygen, less likely to happen. You're putting positive charge on this oxygen, but not as resonantly stabilized, and that's not really resonance stabilized at all. So so that we can have a scheme of favorable conversions to various acid derivatives. So we're going to look at all these reactions in turn, but we can see this. I'm going to draw. So at the top, we have our ROS acid chloride. Over here, we have our anhydride. We have our ester. And so the acid chloride can be easily converted into all of these. Anhydride can be easily converted into all of these except for the acid chloride, not too easily. The ester can be converted into anything below it. And sure, the don't really have an arrow, but maybe the amide might be a little bit hard to make the amide into that. But from there, using SOCl2, which we learned a bit about this last chapter, we can convert a carboxylic acid into an acid chloride. So we can get to the top and then cycle our way down. So if we have any of these derivatives, we can convert it to just about anything else. You just have to think about, what do I have to go from? And so the acid chloride is the most reactive. So we start from here at carboxylic acid or carboxylate, get to the acid chloride, and then we can convert it to an amine or a ester or anhydride relatively easy. So let's look at an example of one of these. How would you convert a acyl chloride into an anhydride, which is the second step? So acyl chloride, you would start by adding a carboxylic acid. So So lone pair going to swoop attack here. We get converted into intermediate here of our, we have our C O minus Cl R O plus C O H, which can resonate between that and C O minus R Cl O. Sorry. Oops. I want to keep my structure the same. R so it can resonate between those two forms. Now from this, when it resonates this form, this can shift down, kick this off. And that gives us, from that reaction, that gives us part of our, we're almost fully at the anhydride, plus there the chloride can then extract the hydrogen, make HCl gas. And there's our let's make HCl. And there is our acid anhydride. So lone pair of oxygen attacks. Now, you say, why wouldn't the alcohol portion of that carboxylic acid attack? Well, if the alcohol portion of it did attack, well, it would be a little bit less stable than intermediate. The advantage of this guy being that this guy is a resonance stabilized. If I had an OH in the center right there, the structure, even though we're closer to where we want to be, the structure is the intermediate is a lot less stable. It has to hang around long enough to kick out the leading group. So having a resonance stabilized intermediate would be a more stable structure than, say, having one that one step closer but not really stable. Okay. Now, showing another example of acyl chloride to form an ester. Now we're probably going to use a base like pyrimidine to neutralize the acid to help force this off. But so same thing. Start with RCOCl. Now instead of an carboxylic acid, we're going to use an alcohol. Lone pair attacks. We get this intermediate, but this is not resonance stabilized. CO minus, moved up, Cl O H. And that's going to be positive. That lone pair swings down, kicks us off. We have our C double bond O, O prime, H plus, and then we need our base, our pyrimidine. Attack there, get that up. Using the base helps stabilize this, helps kick this off to help form our ester. So we're just looking at this. Just the reason why is, like, as you can see, it's the same general mechanism, just with a different reagent, but it's on the same mechanism of looking at forming a amide from acyl chloride. So you're going to use amine, or either an amine, it's excess amine, or some sort of base like pyridine or sodium hydroxide could be used to neutralize the byproduct. So same general thing. Looking at this, we start with acyl chloride. We have some sort of amine, R2. Attacks there, kicks that up. Reversibly, of course. We have our RCO minus Cl and H R. So plus on the nitrogen. We have this then going down, swinging down, kicking that guy off. Precursor for our mid, we're almost there. H plus, we have our R prime and R prime. And then, of course, we use our base. Just say OH minus, or maybe another amine or whatever. It's just going to grab that down, and now we have our amide. As I said, it's not particularly difficult or different from our basic mechanism. So now let's look at, like, anhydrides. Anhydrides doing the same thing. Seeing how an anhydride would jump from an anhydride to an ester. They may be less reactive than chloride, but they're still activated by the same nucleophilic acyl substitution. So RCO. So we have an alcohol with its lone pair attacking here, kicking the lone double bond up. So we have, it's just a much larger structure here now. C double bond O. R prime H. Now, as I said, it's reversible. It could easily jump back to that state, but if it does this, then we have our product. So we're always looking at only the forward reaction, not concerned nearly as much about the reverse reaction, just knowing that the reverse reaction is possible. The reverse reaction is occurring. So we have to do our best to try to force it equilibrium to the right. And then, well, conveniently, we just made a weak base that can now deprotonate that. So we've made a carboxylic acid and our ester byproduct. So RC and our acid. So That's just the nature of, well, our reaction of using an anhydride. And of course, the similar reaction of anhydride to an amide. The only difference being, once again, you use an amine and you get an amide and an acid. You don't need to add base because you're making base as it breaks apart. So I don't need to show the reaction again, but it's the same general premise as the one with the acyl chloride. What about esters are even less reactive than amides, than anhydrides, but they can still undergo ammonolysis. So ammonia and primary amines react okay. Secondary amines react a lot more slowly, and obviously tertiary amines are not going to really react at all. So this is maybe not the reaction you want to try for if you had an option, but you might want to go from an anhydride or from a acyl chloride, but we could very well still do this mechanism. So kick it up, kick it up, kick it up, kick it up. So see, O minus, O R prime, and H3 plus. Lone pair swings down again, kicks this guy off. We have an alcohol, a very basic alcohol from your acidic amide. That R prime O minus comes and deprotonates that, forming your alcohol and your amine, or your amide. So what's going to be that's going to force this to products? Well, having an excess of amine will force that to products. Finding a way to remove that alcohol will force that to products. Basically, all the tricks we used in general chemistry to remove products or add excess reactants to force an equilibrium one way or the other is what we're going to use to make this work in our favor. Doesn't matter what the K is, if we can cause products to form and remove those products, then separate those products, then we're good. So, well, alkoxide is a very strong base and a very poor lead group. Reactions will still occur in nucleophilic acyl substitution in this way. So if you try to do something like a standard SN2, the energy barrier is pretty high. Like, but with nucleophilic acyl substitution, these reactions, I'm going to abbreviate this NAS, we have like a lot of smaller steps with lower energy barriers. This is our tetrahedral intermediate. This is where we form the alkoxide. The alkoxide, and there's our deprotonation to get to a product. So like, there's our addition, there's our loss, And there's our final deprotonation step in all these guys. So if I was just trying to kick them out in one step, too high energy. But if I'm kicking out by making this a 3-step mechanism, you're essentially going to have a lot easier to do. Now we can even go transesterification, so we can switch esters. We can exchange the alkoxide group and the ester. The same mechanism. Now we are going to want to use this in like either some sort of base or acid, but you can do it. So I'm not going to show the mechanism, but you can kind of get the idea. We've seen this. We have O, R prime, and we're going to add a different alcohol in our alkoxide. And you could do this either acid catalyzed, adds to we pronate the O first, the carbonyl O, or you could do this with base catalyzed or base promoted, where this is going to attack here first, kick it up, and then move it down. And of course, then we have to have some way to pronate. But either way, we can use that to form our different ester and our singular alcohol. Once again, it is reversible. All these guys are reversible. So we have to think about this in terms of how do you make one product favored versus the other. So it's always going to be forcing one way or the other. So let's look at the two separate mechanisms. It's just really the order they add. Like, so let's look at this. Because I really want to stick this home. These is a lot of reactions, but they're all so similar that if you understand the concept here, you can save yourself a lot of trouble in memorization. There's not really any memorization that needs to be done. So base catalyzed, they're both catalyzed, either acid or base. Kick that up, make our tetrahedral intermediate. So we have R, C. Oh, jeez. Okay. So we got that. Now, as I said, when this swings down to kick one of these off, if it kicks it, the first group, if it kicks the R double prime off, we're back to our starting material. But if it kicks this guy off, we've moved forward. So we're not going to really worry about the reverse reaction because we're going to assume we have enough base that it's going to, the likelihood is we're forcing it towards products. So we have our correct ester and our new alkoxide base, which can then be pronated by our starting material. And we generate our base. And thus continue the reaction forward. So the base, as long as we have enough HOR double prime and enough base, and we have our base in there, we're going to keep regenerating the base and keep forcing this towards products. As long as we have an excess of our starting alcohol and a little bit of base, it's going to go forward. Now, yeah, so it must be excess to force equilibrium to the right. Acid catalyzed. Let's look at the same. Different mechanism, slightly different mechanism. So, the first step is add the acid. So this is a little different. we have this intermediate CO, which might, of course, equilibrate between that and OH. Now the new alcohol is going to be add to the carbonyl portion and make our tetrahedral intermediate. So R, C, O, H, O, R. H. Positive. Now, so the next step is to regenerate our acid. So some of our excess alcohol is going to then attack and deprotonate that. So now we have RC, OH, OR prime, OR double prime. Now here's where he goes, okay, since that's we're still an acid, we can now repronate. If we repronate at the alkoxide, the second alkoxide, get back to here. Once again, that does not do anything to force us to conclusion. So we're going to assume it's going to pronate there. So an excess of our alcohol is going to force it to products. Excess of alcohol is going to force it to products. Now, we could also pronate the hydroxide, but hydroxide is a weaker base than an alkoxide. So we'd much rather pronate the alkoxide than our hydroxide. So we pronate that. So and then it shifts down. So as it shifts over here to attack there. R, C, OH, O, H, R, prime. Lone pair shifts down. Kick that off as an alcohol. Almost there. We have our intermediate R, O, H plus. Then we have our excess alcohol once again. Deprotonating that. So we always have to regenerate our catalyst. Each step we pronate something, nucleophile attacks, deprotonate. Then pronate again, kicking off the leaving group, deprotonate. So pronate, something happens, deprotonate. Pronate, something happens, deprotonate. But that's just the same general premise of, so same products in the end, just whether you have acidic or basic conditions. Now, sometimes the acid catalyzed version is actually going to be the better version of that, the easier one, even though the mechanism is a little bit more complicated. Okay. Now, hydrolysis of these acid derivatives could either be acid catalyzed or base catalyzed. So if we're going back to carboxylic acid, we could go back that way, either mechanism. So let's look at that. Okay. I'm just looking. So looking at acyl chloride. We can have just water itself attacking this guy. Up. RCO minus. Plus. Swing that back down, kicking off that. Oh. Plus. And then base. Water just deprotonate them. Make hydronium and our carboxylic acid. Now, you can also hydrolyze esters. You can hydrolyze esters. Let's see. Now, if you do a hydrolysis of the esters in the acid form, it is really the opposite mechanism of our Fischer esterification. Now, base catalyzed form is saponification. So I'll show those two mechanisms real quick. Fischer esterification, quick reminder of what that is. It's like, if I remember it right off. I'm not sure I fully remember it right off. Fischer. Oh yeah. That's just literally the reverse of that. So remember, Fischer esterification was, okay, we have our carboxylic acid. Step one, we protonate, which makes, we essentially deactivated the carbonyl, making that a better electrophile, better for our weak nucleophile to attack. So Fischer esterification would have been carboxylic acid, and then alcohol attacks. So H, R prime, H. We have water reforming our acid. RCHOR-OH. That part is definitely still there in the esterification. Then, once again, we protonate again. This time, once again, it could protonate any of these groups, hydroxide, alkoxide, or the other hydroxide. But we're making the assumption here, that if we have one of these guys in large amounts of excess, you're going to force this one direction or the other. Skipping a little bit of a step. Protonating that, and then that swims down. And then, of course, what do? You add water, deprotonate. So Fischer esterification would have been, this is OH, step 1. Protonate the carbonyl, still the same. Nucleophile attacks, still the same. Deprotonate your nucleophile, your weak nucleophile, still the same. Step 2, second half. Protonate the leaving group. Carbonyl shifts down as carbonyl reforms as leaving group leaves. Deprotonate the carbonyl. Same mechanism. The only difference is the weak nucleophile and the and the leaving group have exchanged. Now, base-catalyzed is called saponification. It's a little bit different. That's when we did the soap lab. We're taking a fatty ester, in the soap lab. The hydroxide is then picking that up. Never have more than, well, we're not going to be drawing any more than 4 bonds to a carbon. There, one pair swims down, kicks that out. Again, it's reversible. So what's to say we don't kick out the hydroxide? Well, we could. Now, here's the thing. Because this is a base, this will then deprotonate this to form our carboxylate. Our carboxylate, making this salt. This can be salted out, and then of course we have our alcohol. And of course, to reform this as an acid, then you just protonate. So this is salt. When we add the sodium chloride, we salt this out, and that crystallizes out. So that's all you need for this soap reaction. This is what we did. We have an ester, which is we have the Fischer esterification between our fatty acids and our glycerol, and then we saponify the glycerol to form. Glycerol looks like this: OH, to form this trialcohol, triol, and carboxylates, which we precipitate out. Maybe do a few more. Now we can do the same thing with an amide. We can turn an amide into a carboxylic acid, but an amide, as we're going down there, the scale. Remember, amide was very low reactivity, so you need a very strong acid, a very strong base, and some heating to force this to products. So like, NH2. Oh, we're using some hydroxide, attack there. We need water and heat. NaOH. And heat, and that's going to form our carboxylate. And sodium carboxylate and ammonia. You can do the same thing with strong acid, H2, 3O plus with heat. Form ammonium as a byproduct. One of the things is going to be essentially we can drive these guys off. Now the basic catalyzed mechanism is the same as saponification. The acid catalyzed method is the same as transesterification. So it's really the reason we keep showing these and keeping on these why they're all connected, because they're like if you learn one mechanism, it's the same all throughout. You don't have to keep relearning them. It's just same general thing. Now, I'm going to do one last hydrolysis, which is of nitriles. That's where I'm going to end for today, regardless of how we're doing on time. Just because that seems like a good, appropriate place to end. Nitriles is the only one we really discuss. Nitriles, remember, are RC triple bond N. Well, nitriles, the first thing they do is they're going to react. First, the reaction is going to form an amide. The first step is always to form an amide. And then if you keep reacting, they're going to form a carboxylic acid. So let's see. Now, you only need very mild conditions to convert them to an amide. But if you want to keep going to carboxylic acid, remember we need much stronger conditions. So we could actually favor amide formation by keeping the conditions mild. We just talked about the amides ones, like, oh, we need either a strong acid or a strong base, and we need some heating. So the mechanism here, so R, C triple bond N, water in the presence of base. Well, I don't really. So basically, if I go with in the base catalyzed with water, this is not the mechanism, but just showing like, okay, first you could. This is pretty straightforward, but if you keep going, still on base, you're going to form carboxylate and ammonia. If I do it in acid and water, acid and water, acid and water, we still form the amide. That doesn't change. But the byproducts of the second reaction is, instead of carboxylate, we form the acid, carboxylic acid, and ammonia, the protonated version of ammonia. So, okay, so what is the actual mechanism? What is actually going on? How do we just magically add all those fun things onto there? So let's look at it from basic perspective. R, C, triple bond. So first things first, the base attacks the carbocation. Shift that down to form a hydroxyimine. So COH N minus, which is now capable of depronating water. So we formed a hydroxyamine and H. Now, in the presence of base, we are going to depronate one of those. Once again, reversible. If I depronate that, it's just going to get me back to there. So I have to depronate the other hydrogen. The other hydrogen then puts us at this intermediate, this resonance stabilized, CO minus and that's going to resonance stabilize between R, C, double bond O, and H. And once again, we're always going to be pushing this in the forward direction. Yes, it could reverse and get me right back to there. You can depronate our water and get me right back to there. But if it does, that's not moving me in the forward direction. So there's gets me my R, C, double bond O, and H2. There's my amide. And of course, my hydroxide. So essentially, we attack the positive side with the base, which creates a new negative charge that can be depronated. And we attack we depronate with the base, and then pronate with an acid in a different spot. So we keep on moving it down. And so then, of course, we just talked about the hydrolysis of amide. So there we go. Okay. So that's where we're going to stop for today. We did a lot of different reactions, but they're all super interrelated. So they're all, how do we exchange these guys to here and back? How do we get from the most reactive all the way down to the least reactive? And they're all following a very, very similar mechanism. So don't feel overwhelmed. Slow down, think about it, try to understand how they're related. Try to understand how we're exchanging one for the other. As long as you remember which one is the most reactive, which one's the least reactive, you know, it's easier to go this way than it is to go that way. See how it can exchange. And of course, if you mix SOCl2, you get all the way back up to the top again, and keep on working your way down again. So it's like kind of like a slide. Like you slide all the way to the bottom, and the SOCl2 would be the stairs that's going to lead you back up. Get to the top of the slide again. So hopefully this has been informative. Hopefully you learned something. If you like this, please subscribe, watch for the videos. I'll try to keep on posting them out. Hopefully learn some good all around. And this is the Chemistry Cowboy saying goodbye.